So let's take a few minutes to review some concepts and terms that you probably learned in chemical principles, and that if you didn't, we're going to spend some time reviewing here in organic. We've talked about bonding and the dot structure bonding theory, including ionic bonds and covalent bonds, which can be either polar or nonpolar. There's the octet rule, formal charge, the idea of resonance, looking or determining bond angles in structures, geometry, and you learned more geometries than this in chemical principles, but the five that we'll need are going to be linear, bent, trigonal planar, pyramidal, and tetrahedral, and these will refer to a specific atom center in a molecule. We'll talk about how polar bonds in geometry come together to determine molecular polarity or polar sites in molecules, and how all of that contributes to intramolecular attractive forces like ionic bonds, hydrogen bonding, dipole-dipole attractions, and London dispersion forces. So here on the right, we've got an example of a chemical reaction between acetic acid and sodium hydroxide to produce sodium acetate and water. It's written in the organic chemistry style of writing reactions. And what we want to do is try to draw the structures of acetic acid and of sodium acetate, and apply as many of these concepts on the left to those structures as you can. So take a few minutes and see what you can do. Now we're just going to go through answers at this stage, and this will help you figure out what you might want to brush up on. One thing that we want to realize when we have what we'll later call carboxylic acid or CO2H group is that we have those oxygens both on the same carbon. This is like carbonate or carbonic acid, and a hydrogen on one of the oxygens. For sodium acetate, we have much the same structure. The difference is that we have a formal charge. The one oxygen here that doesn't have as many bonds but has more lone pairs than the other will be negative, and that will be paired off with the sodium. Now, a couple of things to point out here in terms of bonds. We've got, let's think about bond types. There are carbon-carbon bonds and carbon-hydrogen bonds, which we'll consider to be nonpolar, covalent. The carbon-oxygen bonds and the oxygen-hydrogen bonds we'd consider to be polar covalent, because there's a significant difference in electronegativities. Now, there is a difference in electronegativity between carbon and hydrogen, but that's an important one to note that we're going to consider in organic chemistry as typically non-polar bond. Carbon-hydrogen bonds, non-polar. Lastly, we've got an ionic bond between the O- and the Na+ here. And notice that we do not draw a line in between the two. The lines in dot structure bonding theory are for covalent bonds, not for ionic bonds. Draw an ionic bond, all you have to do, draw the two charges next to each other. Now, in terms of the octet rule, all of the atoms are currently obeying the octet rule. Note that that means a maximum of 8 valence electrons. And we specify valence electrons because, of course, most elements outside hydrogen and helium have additional electrons below the so-called valence shell. And the octet rule has the exception in the low end, where hydrogen only has a maximum of 2 electrons. And, of course, there are, on the other end, elements that can violate the octet rule. In terms of formal charges, that would be the negative on the oxygen and the positive on the sodium. elements that are outside what we're going to consider to be their normal bonding conformation for nonmetals, or for metals, simply the ionic form, are going to have formal charges. Now, the idea of resonance is used to explain the fact that we somewhere arbitrarily chose the lower right-hand oxygen to be the one that had the double bond, or the single bond with the extra electrons, and the top oxygen to be double bonded. And really, either of these two structures are viable, what we call resonance forms. In terms of bond angles, we want to recognize that goes along with geometry. So if we think about geometry and the different geometries that are present, this carbon we'd say was tetrahedral, which means that the bond angles between the bonds on that element are about 110 degrees, approximately. We'll say that this carbon, with its double bond to the O, is trigonal planar, and so those bond angles are about 120 degrees. And we'd say that the geometry around this oxygen with a hydrogen and a carbon is bent because of the presence of the lone pair. And since you actually have two lone pairs, then that bond angle is also about 110 degrees. It's a little bit less because the electrons push harder, the lone pair electrons push harder than the bonding electrons do, but for our purposes, we can say it's about 110. Now notice we're missing examples of linear and pyramidal, but hopefully you get the idea. Now let's consider also, when we're thinking about the polarity of bonds, we frequently think about drawing a dipole for polar bonds. So the bonds here between the carbon and oxygen and the hydrogen and oxygen are polar and point towards the oxygen. The same is true of this carbon-oxygen bond. So those individual dipoles will create a molecule that overall we'd say the molecule is polar. It's a little bit complex for us to try to draw a molecular dipole or a dipole moment, because the molecule has so many different atoms in it, but we would want to consider that it is a polar molecule. Anything that's charged, by the way, is going to be exceptionally polar. And we can use this idea to talk about different attractive forces. Now, in terms of intramolecular attractive forces, ionic, of course, is simply the attractive between two opposite charges. So we see that here. Let's recall that hydrogen bonding is the interaction created by a very polar bond, which would be a bond between a hydrogen and a highly electronegative element like an oxygen or a nitrogen or even a fluorine. Now, because fluorine only makes one bond typically, that's not going to be as important for us because we're typically looking at molecules that are more complex, but you learned in chemical principles, so it's worth mentioning. Now, if we consider that water also is polar, hydrogen bonding is actually a specialized dipole-dipole attraction. So a dipole-dipole attraction is when you have a partial plus on one atom in a molecule attracted to the partial minus of another atom in a separate molecule. And hydrogen bonding just gets its own name because it's such an important one in chemistry in general. And we sometimes will show that with a little dashed line, right? This is a non-covalent or intramolecular attractive or attraction. It's not actually a bond per se, even though misleadingly we call it hydrogen bonding. Now we're going to say, by the way, that because this molecule is capable of hydrogen bonding, the acetic acid is protic. That means that it has the hydrogen that is involved in hydrogen bonding. Now note that because the carbon-hydrogen bonds here are nonpolar, they're not going to engage in hydrogen bonding. London dispersion forces, if you recall, are basically the reason that anything else that does not have polar bonds will stick to each other. So if we didn't have that carboxylic acid functional group and we had two ethane molecules, there would be a very slight attractive force between those, and that would be the London dispersion force. So this gives us a quick overview of all the things that we learned in chemical principles, ostensibly, that we're going to need in organic. Now, if you need to brush up on some of these, there's lots of practice in the book. There's guidance on how to draw dot structures, and we'll do some more examples and videos as well.